So twice. You oversell. Okay.
Okay, let's get started with class. Does anyone need the notes that I handed out? Nick, you,
I might see it. So we finished season 7.
anyone else?
Your thoughts? You're the rate every season.
Every season. I think it's
Five is, I can talk about this. 5, like I hate the plot, but they execute it so well.
Okay, yeah, so it's kind of like there's 3 things that we're doing today. I'm going to talk a little bit about section 7.2, maybe for like 25 minutes or so. And then I sent a post out yesterday about the exams. I'm not going to go over the exam. I posted the solution, so you should be able to see how it goes yourself, I suppose. If you have questions about the exam, you can ask me after class, I suppose. But I'll be passing those back. And then the last like 25 minutes or so, there's going to be a quiz. And I know I say this every time, but this quiz, it's a little bit shorter. So I think people will be able to finish it by whenever this class ends, 12:50. Yeah, 12:50. So I don't know. It will go well, like all the other quizzes, and that's kind of it, right? So we're gonna do a little 7.2, and then I'll pass out the exams, and then we'll do the quiz. Okay, and so this section 7.2, this is kind of like the theory part of it. I'm gonna repeat myself a little bit from Wednesday, but this is kind of like the theory component of section 7.2. Next week, we're going to spend more time talking about section 7.2, except we're going to be looking at certain sorts of applications. So I might show some like Python programming where you can use linear algebra to make some sort of like guesses or how people use it in like the industry regarding like principal component analysis or maybe like eigenfaces, which I'll say more about that later on. So this singular value decomposition idea, though, I mean, it's very important. It's like one of the most applied regions of linear algebra. For instance, like when Netflix has like recommendations for users, it's using singular value decomposition technically. So it uses, I mean, it's all over the modern world pretty much. And so so we'll talk about the applications later, but the idea is it's kind of like a more universal version of diagonalization, in the sense that we've been talking about diagonalization, which is where you take a square matrix A and you can write it as the following product of really just eigenvectors and eigenvalues was the main idea. And again, this only works for square matrices, not for like rectangular matrices. So the singular value decomposition, it applies for any matrix A. So if you're given any matrix A, you can express it in the following way. So it's this U times sigma times V transpose, where U and V are going to be orthogonal matrices. And then this matrix sigma is going to consist of what are called singular values, which we're going to define as just being the square root of the eigenvalues. And so really the thing that links, or the idea that links this idea of diagonalization together with this singular value decomposition, is when you're doing the singular value decomposition, you're really going to be doing diagonalization applied to matrices of the form of A transpose times A, right? A transpose times A is always a symmetric matrix. You've actually used this a number of times in various examples throughout the class. And so because it's a symmetric matrix, by the spectral theorem, we know it's diagonalizable, where you can have that the matrices are going to be orthogonal, i.e. like the column vectors are going to be orthonormal, and the inverses are just going to be transposes. So I'm going to talk a little bit about singular values and then maybe go into like what's going on with this equation here. One last thing, so there's kind of 2 main ways of thinking about singular value decomposition in terms of like actually computing it. So one way of thinking about it is this matrix U and this matrix V are really constructed using the 4 major subspaces we discussed in chapter 3. So U is constructed by combining the column space with its orthogonal complement, which is the left null space. And then V transpose is defined by taking the row space and then completing a basis for Rn by adjoining like its orthogonal complement, which is the null space. And so if you know the four major subspaces, you will know how to compute U and V transpose. And then this sigma just comes about from knowing the eigenvalues. That's one way of thinking about it. The way I think about it is more in terms of just this eigen theory, or like the theory of eigenvectors and eigenvalues. It's also going to turn out that V is going to be constructed using the eigenvectors of A transpose times A, and U is going to be constructed using the eigenvectors of A times A transposed. So that's kind of, I think more in terms of the eigenvector interpretation. So that's how I'm going to be looking at this. Okay, so we're going to talk about singular values. What are these things? So before talking more generally about singular value decomposition, we define what the singular values are. That's kind of the only thing we haven't discussed based on kind of this interpretation. It's the only thing we don't know how to compute. And so we're going to consider the matrix A transpose times A. This is always going to be a symmetric n by n matrix, so the eigenvalues are going to be real, and we know we can diagonalize it. And we want to say a little bit more about this as well. So we have the following lemma, which tells us that if lambda is an eigenvalue of A transpose times A, then lambda is going to be greater than or equal to 0. So in other words, we have that A transpose times A is positive semi-definite, right? That's when you have that the eigenvalues are all greater than or equal to 0. So the proof of this is pretty quick, and it uses things that we've discussed earlier, so I feel like it's worthwhile. So we're going to let lambda be an eigenvalue of A transpose times A. And so we're going to have this, I mean, maybe it's a little unintuitive about where this is going to come from. Maybe, I should say maybe a little bit more. So we're going to say it's an eigenvalue of A transpose times A. And I guess I should say what the eigenvector is going to be. So we're going to say like A transpose times A times some eigenvector X is going to be equal to lambda times X. Right, so lambda is an eigenvalue of A transpose times A with eigenvector given by X. It's kind of what I'm saying here. And so what I'm going to be looking at is I'm going to look at A times X, or the magnitude of A times X squared. And so I guess the reason why I'm looking at this quantity here is we know that this quantity is always going to be greater than or equal to 0 because it's the length of some vector. So we know this is greater than or equal to 0. And we also know that we can express this magnitude in terms of dot products, which allows us to introduce an A transposed. So it kind of serves two purposes. It gives you a way of relating, like you have a greater than or equal sign, which is what we've been looking for. And it's going to allow us to introduce the transpose of A as well. And so you can think about this as the following dot product. So this is the dot product given by A times X transposed times A times X. We've done this a number of times, but you can represent dot products as matrix multiplication by introducing the transpose. And so these things are equal to one another. And then you could apply the transpose to flip the order of the multiplication. And so this is going to be equal to X transpose times A transposed multiplied by A times X. And I'm just going to get rid of the parentheses. Right, so this is a transpose here. And so what's nice is now we have the A transposed times A times X, where X is this eigenvector with eigenvalue lambda. So instead of having A transpose times A times X, we can replace it by lambda times X. So this whole thing is equal to lambda times X. And so this is equal to X transposed and then times lambda times X. And then you can flip the order. So this lambda is just a constant, right? So you can bring it out in front. And so this is equal to lambda times X transpose times X. And then we know that X transpose times X, this is just the dot product of X with itself. So you can write it as being equal to the magnitude of X squared. So this is equal to lambda times the magnitude of x squared. And so if I condense this equality, or I should say inequality, from like the first term to the last term, this tells us we have 0 is less than or equal to lambda times the magnitude of x. And so this is going to force lambda to be greater than or equal to 0. Right? I guess I should also, I don't know if I said this explicitly. I know I said it in class, but I don't think I had it written out. Whenever I have eigenvectors, I'm assuming eigenvectors are going to be non-zero vectors. So I'm assuming eigenvectors are always going to be non-zero, which then means this quantity is greater than 0. And so if you multiply by lambda, and the fact that it's still greater than or equal to 0 means that lambda has to be greater than or equal to 0. If lambda was equal to -1, then this would be less than 0. Right. So this implies that we have to have that lambda is greater than or equal to 0. Right. So this is kind of a big deal in that we're saying that A transpose times A is always positive semi-definite, which is a really nice quality to have. Right. Because it's going to allow us to take square roots of eigenvalues and make it so they're not going to be complex. Maybe I'm getting ahead of myself a little bit, but before I move on, any questions about the proof of this lemma? Step. So I was getting ahead of myself a little bit. So one of the nice qualities that we have, because lambda is always greater than or equal to 0 for any eigenvalue, it allows us to take square roots. And that's how we're going to define the singular values. So if we let lambda 1 to lambda n denote the eigenvalues of A transpose times A with repetitions, you can then order these lambdas so that way lambda 1 is greater than or equal to lambda 2 is greater than or equal to lambda n is greater than or equal to 0. So you can order them based on the size because they're real numbers. And so then we can let lambda, or not lambda, sigma I be denoted by the square root of lambda I. Again, we know this is going to be defined because they're greater than or equal to 0, and it's going to preserve the order as well, right? So if lambda is kind of like decreasing as the index increases, the same is going to be true for these sigmas as well. So these numbers, sigma 1, sigma 2, all the way up to sigma n, I guess there should be another sign there, are going to be called the singular values of A. And we talked about singular values already, actually. At the end of section 6.5, when we were taking this matrix S and writing it as A transpose times A, we were making use of this kind of like D matrix, like this D times Q transpose, where we define D to be the square root of sigma or of lambda. And so on the example we did in class on Wednesday, we were actually making use. So these were the eigenvalues and these were the singular values, right? So we've already been making use of singular values. We just haven't defined it yet. And so these singular values, they're pretty important when you're thinking in terms of this like A transpose times A business here. They show up pretty naturally. Okay, so we want to say a little bit more about these singular values. So we have the next proposition. This is all kind of theory and just building up to the singular value decomposition. So it's a number of like smaller proofs that are building up into something larger. So for this proposition, it tells you that the number of non-zero singular values of A is going to end up being equal to the rank of A. So that's kind of relevant to this statement right here, right? When they're defining sigma, it consists of these singular values where you have R of them. R is equal to the rank of whatever your matrix A is going to be. So this rank R here corresponds to the number of singular values, and we're going to prove that now. And so the first thing I'm going to kind of remind you of, this is a pretty big result. We've been using it a number of times, and maybe it didn't seem that important at first, but we've shown before. So we have seen in the past that the null space of A transpose times A is equal to the null space of A. This is something that we proved in class in section 4.2. When we were talking about projections, this was important because you're always looking at A transpose times A inverse within those projections. In that exact same proof, we also showed the following. So we have also seen, that the number of columns, number of columns of A transpose times A is equal to the number of columns of A. And again, you can just think in terms of how size changes based on matrix multiplication. If A is m by n, then this means that we're going to have like an m by n matrix times an n by m matrix. So it preserves the number of columns that we're going to end up having. And so because the null spaces are equal to one another, and you have the same number of columns between the two matrices that you have, this is going to imply that the rank of A is equal to the rank of A transpose times A, right? Just from the fact that rank is really be equal to the number of columns you have subtracted by the dimension of the null space. So as these two things are equal to one another, it implies the ranks have to be equal to one another, right? So this implies that the rank of A is equal to the rank of A transpose times A. This is also going to end up implying that the row space of A transpose is equal to the row space of A, which is actually going to be important later on when we're defining what V in the singular value decomposition is going to be. And so we can go a little bit further here. So this is a little bit more detail. So it's nicer to work with A transpose times A because we know that it's symmetric. Symmetric matrices are very nice. So as A transpose times A is symmetric, we know that it's going to be diagonalizable by the spectral theorem. So it's going to be diagonalizable. Where we have at the, so this is like W, this is saying width. I don't know if I've made that clear. So with the rank of A transpose times A, this is equal to the number of eigenvalues that you have. And in order to find the singular values, you're just taking the square root of the eigenvalues. So the number of eigenvalues is just equal to the number of singular values that you have. So this is equal. Actually, I'm going to kind of condense this. I had it written in terms of two lines here. So the rank of A transpose times A is equal to the number of eigenvalues. This is equal to the number of singular values. But we know that the rank of A transpose times A is also equal to the rank of A. So on the left, you can add another equality where you're saying this is equal to the rank of A. And so this is what we wanted to show, right? We've shown that the rank of A is equal to the number of singular values that you end up having. So again, this will be important when you're finding the singular value decomposition later on. Right, so these two things are equal, and that's what we wanted to prove. And then I'm going to make one note. I said this verbally, but it's important, so I'm going to write it here, and then I'll write it again later on. So as the null space of A transpose times A is equal to the null space of A, this is going to force that the row space of A transpose times A is equal to the row space of A, or equal to the row space of A. Right, because we have that this is the orthogonal complement of A transpose times A, and it's also equal to the null space of A. So it's saying the null space of A is orthogonal to the A transpose times A, which then enforces that A transpose times A has to be, or the row space of this has to be equal to the row space of this, right? Because it's they're orthogonal complements to one another. Okay, any questions about the proof of this proposition at all? Okay, so this is the information that we need regarding the singular values. So we know that the eigenvalues are always greater than or equal to 0. So the square root's going to be a real number over again, which are going to be called the singular values. And we know the singular values, or the number of non-zero singular values, is equal to the rank of A. And I actually made one mistake here. It should be non-zero. It should be non-zero eigenvalues, not just eigenvalues, right? Because, I mean, if you have 0 as an eigenvalue, that would make it non-invertible, which make the rank a little. Okay, so there's only a couple more. I'm not going to be able to go through like everything I want to go through here, but this is now going into like how you actually go about finding the singular value decomposition via this eigen decomposition, which is another way of saying diagonalization. And so in defining the singular values above, we have found that the singular value decomposition is related to the matrix A transpose times A. In fact, what we end up finding is that the singular value decomposition is really just diagonalization applied to the matrix A transpose times A. So we're going to make this more explicit on the next page. And so we're going to set some notation before going through the next part. So we're going to let sigma denote the diagonal matrix consisting of the singular values of A, and we're going to let V be the orthogonal matrix formed by the eigenvectors of A transpose times A. And so because A transpose times A is symmetric, we know that the eigenvectors are going to be orthogonal to one another. And if you make them all unit length, then it means you have an orthonormal basis, which then means that V is going to be an orthogonal matrix. So that works out pretty well. And so how do we go from A transpose times A to this matrix decomposition here, this like U times sigma times V transpose? So you can start with the diagonalization. So the diagonalization we're going to say is equal to V times lambda times V inverse, right? So V is, again, it's the orthogonal matrix formed by the eigenvectors of A transpose times A. And so because V is orthogonal, this V inverse is just equal to its transpose. So it has a really nice inverse description. And so if we want to reach the like the singular value decomposition, instead of thinking in terms of lambda, we want to introduce sigma. So again, lambda consists of the eigenvalues of A transpose times A, whereas sigma consists of the singular values. And so you can go from lambda to sigma by just taking the square root. So you can think about it in the following way. So lambda you can express as being equal to sigma times sigma, right? Or like sigma squared, right? It's just the square root of the eigenvalues. So if I multiply it by itself, you just get the eigenvalues, which will be equal to lambda. And so we have, if you look at the singular value decomposition, right, we have the sigma and we have the V transpose. We have to introduce the U though. And again, we're saying that U is going to end up being an orthogonal matrix. And so we can rewrite this without changing anything, and yet introducing U at the same time in the following way. So U is invertible, so you can introduce like a U times its own inverse within this equality or within this equation without actually changing anything. So how I'm going to do that is the following. So I'm not actually changing anything, but it is kind of a different way of writing it. So in the middle, I'm going to introduce a U transposed times a U, and then sigma, and then V transpose. Again, U is an orthogonal matrix, so U transpose is the inverse of U. So this is just introducing the identity matrix. So you're not actually changing anything going from here to here. And to make it so the parentheses are a little bit more clear, so we have on the left, or like the first three terms, is this V times sigma times U transposed. And then this is being multiplied by U, sigma, and then V transposed. So this is kind of like the decomposition here, right? You have the U times sigma times V transposed. And then this part, so this is kind of like our A. But we want to be able to express this as the transpose of this matrix right here. So one way of doing it is you can rewrite this equality in kind of this weird way. Kind of like we did last class, where you can write this as being equal to U times sigma times V transposed. I kind of messed that up. Right? If I take the transpose of this, that just gives you this here. And then I'm just going to rewrite the exact same thing over on the right. So this is U sigma and then V transpose. Right? So the thing is, like, if this is our A, this matrix we have here is exactly just the transpose of what I have. So like what's inside the parentheses is now the exact same matrix. The only difference is you're applying a transpose here. So this is kind of like your A transpose. Right, so we kind of rewrote this A transpose times A in terms of these orthogonal matrices U and V, and then sigma as well. So this is kind of how you can go from the diagonalization of A transpose times A to the singular value decomposition over here. And so I guess I don't really have, I'm at like 25 minutes. So in class on Monday, I'm going to go a little bit further and say, like, what are these matrices actually going to look like? And how do you actually go about computing them? So I'm gonna stop here for now. Before I stop, are there any questions about, I guess, like any steps that were taken going from here to here? Okay. I'm actually gonna pass out the quiz first, and then I'll pass back the exams while you're working on the quiz. I'm gonna stop recording first, just that way I have more time working